before taking the concept of integral, uh, let me take the derivative of say sine x. Clear? So viewers, what is the derivative of sine x? It is obviously cos x. Clear? Now here we see that this d over dx, is an operator, Okay, so when we operate d by dx on sine x, we get cos x. Clear? We can understand this fact by taking this figure. Suppose this is a box, or we have sine x, and if we operate this sine x, now if we operate this sine x by d by dx, then we get cos x. Okay, so this is the function, say f of x. This is the operator here, and when we operate fx with this operator, then we get an output, and that output is say g of x. Clear? So if we operate sine x with d by dx, we get cos x. So this process is called differentiation. Clear? This process is called differentiation. Now if we write this step in the notational form, then we have d by dx of f of x is equal to g of x. Okay, so the derivative of f is the function g of x. Clear? Now here a question arises that by which operator we should operate this function g of x to get this. It means if we are operating fx with this operator, we are getting gx. Now by which operator should we operate here? Which operator by which we should operate this function g of x to get f of x. Clear? So these two processes are now inverse of each other, because here we are operating this function fx by this operator. The operator is known as the derivative, the first derivative. Clear? So we are getting gx. Now by which operator should we operate this function g of x to get fx? And viewers, this operator is known as integration. Clear? Or we can write it like this. We write it like this by this symbol, and we write here g of x, and we write dx here equal to f of x. Clear? With a constant of integration, say c. Clear? I will explain it later on. This c is called constant of integration. And this is an arbitrary constant. So here we have two things. The first one is that when fx is operated by this operator, we get a new function which is known as the derivative of f. Clear? Now if we operate this derivative of f, which is the function g of x, by this operator, and this operator is called integral of g of x with respect to x. So this is also an operator. This is also an operator. Clear? And this operator is known as the operator of integration. Okay? So if we operate this function g of x with respect to x, we get f of x. Clear? So now let us summarize it. Now if we differentiate this function f of x, we get g of x, and when we integrate g of x with respect to x, we get f of x, and here we have the constant of integration. Clear? Now viewers, so we have the derivative of f equal to g of x, and the integral of g of x is fx plus c. So viewers, this step can now be written as d of dx of fx plus c is equal to g of x, because this step is same as this step. Why? Because the derivative of constant is 0. Okay? So here what we have now concluded, that if we operate f of x plus c with d by dx, we get gx, which is the derivative of this function. And if we integrate this function g of x with respect to x, we get this function f of x plus c. Therefore viewers, we can claim that, or we can define that integration is the inverse process of differentiation. Clear? Differentiation. So hence we can write if d over dx of, say, some function fx is equal to g of x, then the integral of g of x dx is equal to f of x plus c, and this c is called the constant of integration. Clear? And this sign is called the sign of integration, and this integral is known as indefinite integral. Clear? Indefinite integral. Okay? Let fx is equal to, say, tan of x. Clear? Then the derivative of tan x is secant square x, sec square x. Now here's integration is the inverse process of differentiation. So if we differentiate tan x, we get sec square x. Now if we integrate sec square x, we get tan x. If we differentiate tan x, we get secant square x, and when we integrate secant square x, we get tan x. So if we integrate sec square x, we get tan x, and we write this sign. This is the sign of integration, or the sign of indefinite integration, and we write secant square x, this is the sign, then we write this function secant square x, then we have dx. This dx means that we are integrating with respect to the variable x, clear, and we write tan x, clear. So secant square x when integrated gives tan x. Now here we cannot simply write tan x, so we have to write a constant of integration also. Why? Because if we differentiate tan x or tan x plus c, we get secant square x, clear. So the integral of secant square x dx is tan x plus c, or in other words we can say that the indefinite integral of secant square x is tan x plus c, and this constant of integration may take any real value here. So c belongs to the set of real numbers, clear. So here we can write if we differentiate, it means if we differentiate tan x, we get sec square x, and if we integrate secant square x, we get tan x. And because we have to mention the constant of integration, so here we can write tan x plus c, or here also we can write tan x plus c, but since the derivative of tan x is secant square x and tan x plus c is also secant square x, clear. So this is the meaning of finding the integration of a function. So let us take some more examples. Now we can write, say, d by dx of e raised to x is equal to e raised to x. The derivative of exponential function is the exponential function itself, clear. So it means that when we integrate this function, we get this function. So when we differentiate it, we get this function, clear. This is differentiation. And if we integrate, then we get this function e raised to x and plus c. So therefore we can here write e raised to x plus c. When differentiated, we get e raised to x, because the derivative of this constant is 0 and c belongs to the set of real numbers, clear. So therefore we can write here the derivative of, say, log x plus c is equal to 1 over x. So by definition, integration is the inverse process of differentiation. So if we integrate 1 over x with respect to x, it gives log x plus c, clear. Similarly, viewers, now viewers, here more strictly we should write this expression as 1 over x dx is equal to log of absolute value of x plus c, clear, and where this x is not equal to 0, clear. Viewers, let us take some more examples. See what is the derivative of this function, say 3x square plus 4x cube. what is the derivative? Now obviously we know that the derivative is 6x plus 12x square. Now this is the operator and this is the function, clear? And this is the derivative, 6x plus 12x square. So this implies that by the definition of integration, that integral of this function 6x plus 12x square with respect to dx is equal to 3x square plus 4x cube plus a constant of integration. So here's these two expressions are equivalent. Okay, so these two expressions are equivalent. So here this c is the constant of integration and c belongs to the set of real numbers. So thus we can say that this function, the integral of this function, the integral of 6x plus 12x square is 3x square plus 4x cube plus c, and c can take any real value. So this the integral of this may be 3x square plus 4x cube plus 1, or 3x square plus 4x cube minus 6, and so on, and it depends on the value of c, because c can take any value. So this function can have an infinite number of indefinite integrals. Clear? Now viewers, we are going to see some symbols regarding integrals. Clear? Let y equal to fx be a function. Clear? And this is a differentiable function, and the derivative of y dy over dx is, say, f prime of x. Clear? So therefore we can write dy equal to f prime of x dx. Clear? So therefore we can if we write this expression in terms of or we can say that the integral of y with respect to the integral of y is the integral of dy, I'm sorry, it is dy, then we can write it as f prime of x dx. Clear? And we can write it like y equal to f prime of x dx. Clear? So this is an important concept, viewers. This is f prime, and here we must keep one thing in mind, that integral of say dy is y, similarly dx is x, and only if the variable changes here, then we have equal to, say here dt, it is equal to t, the integral of dx is x, the integral of dy is y. So here we have the integral of dy as y. Clear? Viewers, suppose we have dy over dx equal to, say, some function g of x, then this expression can be written as y is equal to the indefinite integral of g of x with respect to x plus c. Clear? So we have to remember this concept also, because the derivative of y with respect to x is some function and the function is g of x. So by making use of the definition of integration, and which is integration is the inverse process of differentiation. So if we integrate g of x with respect to x, then we get y. Clear? Now viewers, we are going to study some properties of indefinite integral, and the first one is the process of differentiation and integration are inverses of each other. In fact, we have used this definition for the process of integration. So let us now here we have the derivative of f of x is equal to f prime of x. Now this is the operator, so the derivative of f is f prime of x. So it means that the integral of f prime of x dx is equal to fx plus c. Clear? So the process of differentiation and integration are inverses of each other. Clear? And here c is the arbitrary constant, and c belongs to the set of real number. Clear? The second property is, suppose we have to find the integral of the indefinite integral. Viewers, always remember this sign is known as indefinite integral. Indefinite integral. And suppose we want to find the indefinite integral of a sum of two functions, then this indefinite integral will be distributed over these two functions. Clear? So we can write here integral of f of x dx plus integral of g of x of dx. Clear? Here we can take an example. Suppose we have to find the integral of indefinite integral of sine x plus say e raised to x. Then what does it mean? It means we have to write it like this. We first write the integral of sine x dx plus then we'll write the integral of the exponential function. Clear? So this is the meaning of this property. Clear? Now the third property is, for any real number, say k is any real number, we have the integral of k times of some function fx dx can be written as k times integral of f of x dx. Clear? So it means if we have an integral, say 2 times of e raised to x dx, then this can be written as 2. We can take 2 outside this sign, and we have 2 times of e raised to x dx. Clear? And then we have the integral of e raised to x dx as 2. The integral of e raised to x is e raised to x plus say c. Clear? And then we write this expression as I am writing it here. So this expression can be written as 2 times of e raised to x plus 2 times of c, and this can be written as 2 times e raised to x plus 2c can be replaced by some other constant of integration, say c1, and c1 is 2 times of c. Clear? Now viewers, the properties, the last two properties which we have just discussed can be summarized in this single property. And if we have, say, the indefinite integral of k1 f1 of x plus k2 f2 of x and so on, and say we have kn fn of x. Clear? And we have to find the integral of the indefinite integral of, say, this function. So this function, the integral of this function can be written as, we can write k1 times the integral of f1x dx, k2 times integral of f2x dx, and so on up to kn times integral of fn of x. Clear? Here we can quote an example, and if we have, say, the integral of, say, 3 cos x plus 5 e raised to x minus 6 x square. Clear? So here's, by making use of this property, we can write this expression as, we take 3 outside. Here k1 is 3, k2 is 5, and k3 is minus 6. Clear? And this is f1, this is f2, and this is f3. Clear? And this can be written as 3 times of integral of cos x dx, then plus 5 integral of e raised to x dx, and minus 6 integral of x square dx. Clear? Now viewers, I am going to discuss some elementary results in integration, and the first one is, say, if we have a function fx is equal to x raised to n. Then here I will be discussing first the derivative of f. Clear? So we know that the derivative of f of x is nx n minus 1. Clear? So in differential calculus, we saw that the derivative of x raised to n is nx n minus 1. Now let us see the integral of x raised to n. Now this expression can also be written as d by dx of x raised to n is equal to nx n minus 1. Clear? Now here's this is the operator, this is the operator, this is the function, and this is the result or the outcome or the output. Clear? Or the function. The derivative of x raised to n is nx n minus 1. Clear? Now we know that integration is the inverse process of differentiation. So if we integrate, when we differentiate this function, we get this. Now we'll integrate this function. Clear? With respect to x. So if we integrate this function, we must get this function. This is x raised to n. Clear? Now viewers, by this result, we are able to write this expression. So these two expressions are equivalent. Clear? Now if I replace n by n plus 1 in this expression, I am going to replace n by n plus 1. So what I am going to get, let us see. So here we have n plus 1, and here we have n plus 1 minus 1 of dx, and here we have n plus 1. Clear? Now yes, this is a constant, so we take it outside the integral sign. So we have x raised to n. This 1 and 1 get cancelled, and we have x raised to n plus 1. Now taking this n plus 1 to the denominator here, so we have x raised to n dx is x raised to n plus 1 divided by n plus 1, and along with the constant of integration. Clear? So here we have arrived at a very important result, and the result is the integral of the indefinite integral of x raised to n dx is equal to x raised to n plus 1 divided by n plus 1. And here we must keep one thing in mind, that this formula is not valid for n is equal to minus 1. So n should not be equal to minus 1. Clear? So now we can summarize these two results in the form that the derivative of x raised to n is nx n minus 1, and the second one is the integral of this function x raised to n dx is equal to x raised to n plus 1 divided by n plus 1 plus c, provided n is not equal to minus 1. Clear? Now with the help of this result, we are now going to derive some important results. Now let n is equal to 0. So here we get x raised to 0 dx is equal to x raised to 0 plus 1 divided by 0 plus 1 plus c. Clear? So yes, now x raised to 0 is 1, so we have 1 dx, and this is x raised to 1, this is 1 plus c, and whereas we have the integral of dx is equal to x plus c. So this is an important result. Clear? Similarly, we can write the integral of dy as y plus c, or integral of dt as t plus c. Clear? Now yes, let us write n is equal to say 2. Then we have the integral of x square dx is equal to x raised to, here we have 2 plus 1 3, and this is 2 plus 1 3, so x raised to 3 divided by 3 plus c. Clear? Similarly, x raised to 10 dx is equal to x raised to 11 divided by 11 plus c. Clear? Now viewers, let us take the integrals of inverse trigonometric functions. We have already seen that the derivative of sine inverse x is 1 divided by 1 minus x square. Clear? Now by using the definition of integration, integration is the inverse process of differentiation. So we can write the integral of 1 minus x square, square root of 1 minus x square dx is equal to sine inverse x plus c. And similarly, we can define the formula for other trigonometric, inverse trigonometric functions. Let us take one more inverse trigonometric function and say we have the derivative of cot inverse of x. So the derivative is minus 1 over 1 plus x square. So here's by the definition of integration, we can write the integral of minus of 1 plus x square dx is equal to cot inverse of x plus c, and if we take this negative sign to this to the right hand side, we see that normally we do we do not take this negative sign here, and we directly write it as minus cot inverse of x minus plus of c, because by using the definition of integration as the inverse process of differentiation, if we write the integral of negative of 1 plus x square, then we should write it as cot inverse of x plus c, and if we take this negative sign here and here, then this negative sign remains here, but we replace the constant minus c by some other constant, say c. Clear? Or we can write it here, say c1. Clear? So the negative c is replaced by c1. Clear? So similarly, if we take the derivative of say tan inverse of x, then we have 1 over 1 plus x square, and this can be written as 1 over 1 plus x square dx is equal to tan inverse of x plus c. Clear? Now viewers, we have the derivative of cos x as minus of sine x, so we take this negative sign here, so this expression can also be written as minus of cos x. The derivative of minus of cos x can be written as sine x. Okay. Now the integral of sine x, the integral of sine x dx is equal to minus of cos x plus c. Clear? Okay. Viewers, we have the derivative of log of x is equal to 1 over x. So this implies that the integral of 1 over x, the integral of 1 over x dx can be written as log of mod of x plus c. Clear? Similarly, we have the derivative of say a raised to x, the general exponential function here is equal to log a times a raised to x. Clear? So this expression can be written as d by dx of a raised to x divided by, because this is a constant, so we can write it here, and we have this expression. Clear? So the derivative of a raised to x divided by log a is a raised to x. So therefore, by the definition of integration, the integral of a raised to x dx, the integral of this function is equal to this one. So this is equal to a raised to x divided by log of a plus c. Clear?